Today we learn about wind energy generation system, WEG. So we start with introduction. Wind is a byproduct of solar energy. Approximately 2% of the sun's energy reaching Earth is converted into wind energy. Wind is the atmospheric flow and wind energy is the kinetic energy of air. The wind energy is highly dependent on the local average wind speed and it is intermittent. A wind turbine is a rotary device that extracts energy from the wind. Wind power is renewable and produces no greenhouse gases during operation, such as carbon dioxide and methane. Number 2. Where does the wind come from? So let's see this figure. So the hot air rises from the low pressure latitude. So it will go to the high pressure latitude. So hot air rises, leaving low pressure area behind. Okay. So this hot air rises and leaving the low pressure and go to the high pressure latitude. So it will sink back and move to the low pressure area. So this process will continue and it will produce the air. So this is upper air current, downdraft to the high pressure, from the high pressure go back to the low pressure. So this one we call updraft. So upper air current is in this direction and this is the lower air current. Okay, when the hot air rises, it goes to the high pressure area. So from this area, the cool air sink go back to the low pressure area. So flow of air are using this direction. So hot air rises leaving low pressure area behind. At different latitude, cool air sink and move back to the low pressure area. So the wind speed changes with distance upward. So this is the example of the surface wind vector and the magnitude in meter per second. This is from the 0 degree east to 100 degree east, 260 degree west and 50 degree west. Okay. This one represents the wind speed in meter per second. This is the latitude. The average wind speed for Malaysia is about 0.5 to 2.5 meter per second. Okay. Very low wind speed. So this concept is similar to the low pressure and high pressure area. So during January, of course, on the north side, there will be a winter. So this area will have high pressure. So the cool air will sink and go to the low pressure area. But on July, the south part will be cool. So the wind will flow from high pressure area to the low pressure area. So this figure shows a typical variation of wind speed from Earth's surface at different sites. So we have 3 sites here: city core, outskirts and open land. If you refer to this city core, so the wind speed here will be at 10 meter per second at height about 500 meter. But for the outskirt, to reach this 10 meter per second, the height is about 400 meter, which is less than city core. But for open land, the wind speed can reach 10 meter per second at very low height, which is less than 300 meter. So this is because this is the open area or the agricultural area. So the wind speed is high at low height. Number 3, wind rose chart. It is very important to study the wind profile of a prospective wind energy generator site. A wind rose is a chart which gives a view of how wind speed and wind direction are distributed at a particular location over a specific period of time. It is a very useful representation because a large quantity of data can be summarized in a single plot. There are many commercially available software to plot wind rose chart. So data from wind speed sensor with direction, well known as anemometer, are sampled and logged. Usually logged for 1 year before transfer to wind rose chart for analysis. Here is the example of the ultrasonic type anemometer. So this type of anemometer are using 2 axes, which is it can measure the horizontal wind speed only. Okay. Here in the figure we have 4 transducer. So this 4 transducer will measure the wind speed and the wind direction. So this technology using ultrasonic wind speed measurement technology. So this anemometer can measure the wind speed up to 60 meter per second and can measure 360-degree wind direction. It also have a low startup speed. So these 4 transducer alternately send and receive ultrasonic pulses to each other. Another type of anemometer we call cup type anemometer. So this one using this cup to measure the wind speed, and here the wind vane is to measure the direction of the wind. So this is the example of the wind rose chart. So in this figure, this area represent the frequency of the wind, and this color represent the wind speed. So in this area, most of the wind come from the northwest, and most of the wind are between 2 to 4 meter per second and 4 to 6 meter per second. Only a few moments that the wind speed go up to or greater than 10 meter per second. So overall, in 1 year, the mean speed is 2.59 meter per second. The peak frequency is about 18.64% here, 18.64%. The peak direction is from the northwest. Percent comes 8.14%, and come defined as less than 0.5 meter per second. So this figure shows the wind distribution. So below 100 meter, so this is the surface boundary layer and the bottom layer here. So this is the atmospheric boundary, which is between 0 to 1000 meter. So above 1000 meter we call free atmosphere. So this is the vertical distribution of the wind speed, which is the wind speed will be higher at the high height. So the higher the height, the higher the friction. So in this area between 100 meter to 1000 meter is a higher friction layer. So we have 3 distributions: surface boundary layer, bottom layer and the higher friction layer. So the wind speed V at height Z above the ground can be estimated by V equals to V1 multiplied with Z over Z1 to the power of 1 over N, where V is the wind speed at the height above ground level Z, V1 is the reference wind speed at the reference height, which is what we call Z1, and N is the roughness of the ground surface. So to know the roughness of the ground surface, it divided into a few conditions. Condition number 1, which is flat meadow. Flat meadow, the roughness is between 7 to 10. So 1 over N will be 0.10 to 0.14. Coarse, also same thing, and 7 to 10. This is dash. 7 to 10. Okay, same thing. But for agricultural field, the roughness reduced between 4 until 6. This is also dash. Okay, so 0.17 until 0.25. Next one, urban area. So the roughness between 2 until 4. So 1 over N, we get 0.25 until 0.5. Let's see example to calculate this wind speed. Example, anemometer reading at 10 meters above the ground at two different places, which is Green Energy Research Center Shah Alam, Malaysia, and Padifi Sekinchan, Malaysia, are similar, 3 meters per second. So this is at 3 meters above the ground. Estimate the wind speed at 30 meters above the ground at each location during the measurement. What can you conclude from the result? Okay, so conclusion, first we calculate. We know that the speed at 10 meter per sec at 10 meter is 3.5 meter per second, and the reference for Z is 30 meter. Okay, so GRC UIT and Shah Alam is an urban area. So this urban area we use roughness 2 to 4. So using the equation, V equals to V1 multiplied with Z over Z1 to the power of 1 over N. So the wind speed at GRC is 4.6 meter per second. 2, V equals to V1 multiplied with Z over Z1 to the power of 1 over N. So this is for the roughness of 0.5. So you get 6.06 meter per second. So using two roughness, this one for the first equation, using the first roughness, to second equation using the second roughness, because this equation is based on the 2 to 4 roughness. Okay, so this is 2 to 4, which is 1 over N1 means 1 over 2. So you get 0.5. So this is 4. 1 over 4, you get 0.25. So the wind speed at GRC at height 30 meter is between 4.6 until 6 meter per second. Now we calculate using same equation for paddy field Sekinchan. So this paddy field Sekinchan is agricultural field, which is the roughness between 4 to 6. So this roughness is 1 over 4 to 1 over 6. So we get the wind speed between 4.2 meter per second until 4.6 meter per second. So if you compare these two locations, you can see that GRC produce the wind speed is much higher compared to the paddy field, at height 30 meter. It can be concluded that the wind speed is vary depend on the ground surface condition. The higher roughness of the ground, the slower the wind speed above the ground. So Padi Fisikinchan has the lowest wind speed at height 30 meter. GRC Shah Alam has the highest wind speed at height 30 meter. So wind turbulence. So wind turbulence usually produced behind the tall object. So example in this figure is the wind turbulence behind the hill. So turbulence and fluctuation of wind direction. So it produces turbulence here. Another one is turbulence before the building and after the building. So recommended to install the wind energy generator system which is greater than this distance, which is 10 to 20 times of the height of the building. And also in here, if you want to install the wind energy generator system near to the building, it should be 2 times of the building. So this turbulence also occur here before the forest and after the forest. So it's recommended to install the WEG system which is more than 15 HS, which is greater than 5 to 16 height of the tree, or 5 meter apart before the tree. Number 5, wind speed measurement. So anemometer is used to measure wind speed. Wind speed is usually measured every 10 minutes. Average is at least 1 year. Anemometer are installed every 10 meter over 20 or 30 meter mass height. So example here, this is a lightning rod. We have 2 anemometer here, cup type. So the first anemometer at 20 meter height and the second anemometer at 30 meter height. So this is wind vane to measure the wind direction. This is mask. This is cup anemometer and this is stay. So this is to hold the mask. This is the data logger to log the data of the wind speed and the wind direction. And this is the bottom plate. And this is the anchor to hold this structure. So again, example of the anemometer and the wind vane. Number 6, wind energy. Wind energy is usually kinetic energy from wind is calculated as E unit in joules equals to 1 over 2 m. M is a mass in kilogram multiplied with velocity to the power of 2. So velocity unit in meter per second. And then we divide the period of time E over T equals to 1 over 2 m over T v squared. So E over T equals to power equals to 1 over 2 m over T v squared. However, m over T it also can be expressed as m over T equals to rho A V. So rho kilogram per cube meter multiplied with A is the area multiplied with velocity in meter per second. So the power will be 1 over 2 multiplied with rho multiplied with A multiplied with V to the power of 3. So we substitute this equation into this equation and then we get this equation. So this is equation. So it comes from the kinetic energy. However, not all power from the wind can be extracted by the wind turbine. The maximum limit is 59%, which is also known as best limit. Therefore, power from the wind turbine is P wind turbine equals to Cp multiply with 1 over 2 multiply with rho multiply with A multiply with power of 3. So this Cp is the limit, usually 59%. A is the area which is swept area by the wind blade, which is in diameter. So A equals to pi d over 2, this is diameter, okay, divide by 2 to the power of 2. So therefore, P wind turbine equals to Cp. You substitute this equation into this equation, you get Cp equals to 1. Cp multiply with 1 over 8, multiply with pi, multiply with d squared, multiply with rho, multiply with v to the power of 3. Where Cp is the output power coefficient of the generator, theoretical maximum limit is 0.59, typical average of 0.25 for small machine and 0.35 for large machine. D is diameter of the blade, unit meter. V is wind speed, unit in meter per second. Rho is density of air, which is 1.204 kilogram per cube meter for dry air at 20 degree and 101 kilopascal. So this table shows the relationship between air temperature and the density. So air density, so the lower the temperature, the air density will become higher. The higher the temperature, the air density will become lower. In summary, based on the above formula, the power produced by the wind turbine depends on the length of the blade, speed of the wind, V, which also depend on the height from the ground surface, output power coefficient, Cp, air density, which it also depends on the air temperature. Number 7, annual wind energy production. Wind generator do not produce power at all the time. Sometimes the wind is too strong and sometimes not strong enough. It is important to predict how much energy on a daily, weekly, monthly or yearly basis the generator will produce. Two methods to estimate annual energy production, which is Roughness estimation and power curve. Okay, we start with rough estimation, 7.1. So the total energy production can be estimated using the equation E generated equals to Cp multiplied with 1 over 8, multiplied with pi, multiplied with d squared, multiplied with n, multiplied with rho, and multiplied with total mean wind and wind speed in hourly value. So Vi means wind speed hourly value. Make sure you the power of 3, and it's a number of hours, which is n equals to 8760 hours for 1 year. And Cp for annual efficiency factor typically 0.25. So this 0.25, remember back, 0.25 is for the small machine. Another method is by using power curve. The power curve of a wind turbine is a graph that indicates how large the electrical power output will be for the turbine at different wind speed. So typical value, we have cut in speed, which is the wind speed to start running of wind turbine is called as cut in wind speed, typically between 3 to 4 meters per second. A rated speed, which is 12 to 16 meter per second, depends on rated capacity of the wind turbine. And the cutout speed is the speed to stop running the turbine, is called as cutout wind speed, typically 24 to 25 meter per second. Having a cutout speed is a safety feature which protect the wind turbine from damage. So here is the example here. This is a cut-in wind speed when the turbine start to rotate, and this is the rated wind speed. So at this condition, the power will start to become constant. So typical characteristic of a wind generator. So this is the ideal power output, and cutout wind speed, which when the turbine is stopped running. Okay. So this is the ideal power output, and this is the inefficiencies. So inefficiencies, in area of low wind speed, it is important to install machine with low cut-in wind speed. So if the area have a low wind speed, so we need a turbine or machine, WEG machine that have a low cut-in speed. When the motor reach its rated output power, so this is the rated output power. Some inefficiency are artificially introduced to limit the power to its rated value. So this is the area of inefficiency. At very high wind speed, the machine may be totally stopped. So cut out wind speed. So they totally stop here, which is cut out wind speed. Energy estimation using power curve from manufacturer to estimate the yearly energy generated for the turbine. It requires wind speed histogram. A bin range of 1 meter per second is adequate. So this is the bin range or the wind speed. The data of wind speed are sampled every 1 hour. So energy generated equals to, this is total number of power multiplied with number of event in hours. So P curve is the power obtained from the power curve at mid-range wind speed. And Ni is the number of event or hour that will speed at mid-range occur within the duration period. I is the mid-wind range number. So this one we can refer to the histogram. Okay, we will later learn about the histogram graph. So example here is the power curve. So this power curve, in this area we have capacity factor, which is average output power, divide with rated power, okay, from 0 to 0.8. So here we have average wind speed divide with rated wind speed between 0 to 1.0. And this area is the cutout speed divide with rated speed. So this figure estimate of expected average output power of wind turbine. Assume a wind frequency distribution for wheel-bull shape factor K equals to 2. This is one of the example of the power curve. Another one is in this shape. Okay, so we have two power curve. Sometimes represent in this condition power versus wind speed. Another one by using this curve. So if the power curve is not given, then you can estimate energy generated using general power curve method. Usually wind turbine manufacturers give the following information. Number 1, rated power at rated wind speed, and number 2 is cut out wind speed. The above general power curve require information on average wind speed. The most accurate method to obtain wind speed is on-site measurement at the proposed height of the turbine. The method of bins provide information about how many hours during the measurement period the wind speed was within each wind speed bin range. This data constitutes a wind speed frequency distribution That is, it shows the frequency of occurrence of wind speed within each range. The word distribution refers to the fact that the wind speeds are distributed over a range of values from 0 to whatever the maximum wind speed at the site is. So this is the example of distribution histogram, like I said before. So this is the wind range 0 to 1 meter per second, 1.22 meter per second, 2 to 3 meter per second. This is the number of hour. Example here, for wind speed between 0 to 1 meter per second, so number of hour is 64 hour. Example here, from wind speed 6 to 7 meter per second, number of hour is 21 hours. So the mean wind speed over the whole measurement period, Vm, can be calculated in the following way. Vm equals to V1 multiplied with N1 plus V2 multiplied with N2 and so on over N1 plus N2 plus N3 and so on. So this Vm represent the mean wind speed over the whole measurement period, meter per second. Vn or V1, V2, V3 and so on, the midpoint of the nth wind speed being in meter per second, and n is the number of hours counted in the nth wind range. So let's see the example using this equation. Example number 1. Wind data was collected for 31 days as shown below. So this is the bin range in meter per second between 0 to 1. So mid-bin range is the average 0 to 1. So the average is 0.5. So 1 to 2, the average is 1.5. 2 to 3, so the mid-bin range will be 2.5. 3 to 4, 3.5. So it becomes the middle one. So between 0 to 1, number of hours is 5. And the wind speed between 1 meter per second to 2 meter per second, number of hours is 19 hours. So you total up all number of hours here. So you get 744 hours. So this value is from mid-bin range 0.5 multiplied with number of hours. So that one represent this equation. V1 multiplied with N1. So 1.5 multiplied with 19, you get 28.5. 2.5 multiplied with 82, you get 205. And then you total up all. So you get 3,632. So mean wind speed Vm 3,632 divided with 744 hours. So the mean wind speed is 4.882 meter per second. So this equation, that value come from this equation. So example number 2. A wind energy generator system is planned to be installed at Kuala Perlis. A 1-year wind profile and expected output power at the prospective site is shown in table A. So this is a wind range between 0 to 1, and then 1 to 2, then 2 to 3, and then you need to find the mid wind speed. So 0 to 1 you get 0.5, 1 to 2 you get 1.5, 2 to 3 you get 2.5, and this is the output. So this output comes from the power curve. Okay. So output comes from the power curve, and this is the duration that measured on the site. So design the wind energy generator system by determining rated power, cut-in speed, and rated wind speed of the wind turbine. Number 2, total energy generated for 1 year in megawatt hour And number 3 is the capacity factor, CF, and comment on the value obtained. So solution from the graph to find the rated power. So you imagine in this table you convert into the graph, you can see that the rated power is 8,000. Okay, remember back the power curve graph. So the rated power is when the power start to become constant. So this is the rated power. So in this case, 8,000 watt. Okay, 8,000 watt here. So it become constant. And then rated with speed when the graph start to become constant, which is the power start to become constant at speed 13 meter per second. Don't take this mid-mean range. So it start to become constant at 13 meter per second. So that cut in with speed, which is the turbine start to rotate and produce power. So you find the speed, which is 4 meter per second when the wind turbine start to produce the output. Okay, so the answer is 4 meter per second. Don't take mid wind speed. Take the value from this wind range. Start from 4 meter per second. The wind turbine start to produce power or start to rotate. So from the value number 2, total energy generated for 1 year in megawatt hour. So all of these come from the measurement, and then number of hour also from the measurement, and then calculate the energy. Energy, which is power multiplied with duration. So 0 multiplied with 450, so you get 0. Here 250 multiply with 595. So you calculate, total up all, and then you get 25246,250 watt hour annually, and then convert into megawatt hour. So you get 25.24 megawatt hour annually. The last question, the capacity factor and comment on the value obtained. So the capacity factor, so energy annually 25246,250, and the P rated is 8,000. So you calculate the capacity factor. So capacity factor you will learn here in the equation. Okay. Page 52, capacity factor is defined as actual power generated multiplied with duration. So usually we calculate yearly, divide with rated power, multiply with duration. So the WEG is economically viable if CF at least 20%. For offshore, it's between 30% to 40%. So go back to the example. So this is energy annually. So power already multiply with the hours. So you get energy. And then you divide with P rated 8,000 multiply with number of hour in 1 year. Number of hour in 1 year is 8760. So you get 36%. So the WEG is economical because CF greater than 20%. So this type of statically distribution can be modeled mathematically and is called a Wilbur distribution.